Hello friends, welcome to my channel Studying Sprout with a new chapter, that is electricity. We'll start with electric current and electric circuit. So first of all, we need to know what is electric current. We all know that flowing river water constitutes charge. So our next question should be, through which bodies charge flows? Do all bodies constitute electric current in it? And the answer is no. Electric charge flows only through conductor, and if charge flows, there is an electric current in it. And here many times we have come through charge. So first of all, we'll clear this confusion as to what is charge. Okay, charge is a fundamental particle in an atom. It may be positive or negative depending. Okay, like charges repel each other, they are always unified as negative and positive charges. Like charges will repel, and unlike charges attract each other. Okay, these are the features or qualities of a charge. Okay, Coulomb, SI unit of charge is Coulomb. Okay, which is denoted by C, capital C, and 1 Coulomb is equal to charge approximately present upon into 6 into 10 to the power 18 electrons. So it means then 1 Coulomb charge is equal to 6 into 10 to the power 18 electrons. Okay, charge on 1 electron is 6 into 1.6 into 10 to the power minus 19 Coulomb. Okay, so these are the datas which you should remember. Okay, because in numericals it will be easy for you all. So now I hope charge is clear, and now we'll move further. You might have seen a torch. Okay, this torch gives light. It gives light because of flow of charge. Okay, and this job is done only when the switch is on. Now the purpose of switch is to provide a conducting link between the cell and the bulb, and this closed conducting link is called circuit. What is called electric circuit. And now I'll tell you what is the exact definition of current. Okay, so here I have underlined all the main points in yellow. You can underline it in your book, so it will be easy for you. Okay, so electric current flows through a conductor. Okay, so the main definition which we are going through electric current is expressed by the amount of charge flowing through a particular area in unit time. Okay, or you can also say it in other words, that is, it is rate of flow of electric charges. Okay, here only you can do the formula. You can take out the formula of electric current, and electric current is denoted by I, and so it is amount of charge flowing per unit time, so it will be Q by T. So formula of electric current will be I is equals to Q by T. Okay, I hope it is clear. Now the next is, what is the SI unit of current? Okay, SI unit of current is ampere, and you have seen what is SI unit of charge. SI unit of charge is Coulomb. SI unit of current is ampere, and it is denoted by capital A. 1 ampere is equals to 1 Coulomb per second. It in 1 ampere 1 Coulomb of charge per second is passed. Okay, it travels. Here it is even. Okay, then 1 microampere is 10 to the power minus 3. Okay, is equals to 10 per minus 3 ampere, and 1 milliampere is 10 to the power minus 3 ampere, and 1 microampere is 10 to the power minus 6 ampere. Okay, and this French this ampere is word is came from French scientist André Marie Ampere. Okay, now we'll take a look on this closed circuit. Okay, this is a circuit. You should understand the circuit as it numericals comes from this. Okay, this is the ammeter, this is the bulb, this is the direction of flow of current flows through it. Okay, and this is the terminal. Okay, and this is the plug. Okay, plug key, and this is the cell. Fine, and as you know that current always flow from positive terminal to the negative terminal. Okay, so this is positive terminal and this is negative terminal, so it flows from current flows from positive terminal to negative terminal. Okay, diagrams comes in the exam to draw the diagrams. Okay, for numericals, so you take a look and then remember. Okay, now I want to tell you that the current is measured by ammeter. Through this ammeter only current is measured. So the next question is, what is the unit of current? Unit of current is ampere. Okay, ampere, just now I told you, and it is denoted by the capital A. Now calculate the number of electrons constituting 1 Coulomb of charge. So number of electrons in 1 Coulomb of charge, I told you it is 1.6 into 10 to the power minus 19 coulomb. It is a negative charge. Okay, sorry, it is asking calculate the number of electrons constituting 1 coulomb of charge. One number of electrons it is asking, so it is 6 into 10 to the power 18 electrons. Okay, I told you the charge on one electron. Okay, charge on one electron is 1.6 into 10 power minus 19 coulomb, and the number of electrons in 1 coulomb charge is 6 into 10 power 18 electrons. Okay. Now our next topic is electric potential and potential difference. So first of all, we'll be discussing what makes electric charge to flow. So here they have tried to explain us with example of how water in a horizontal tube flows. To make the water flow through the tube, one end of the tube must be connected at a higher level, creating a pressure difference between the two ends of the tube. And this is how water flows in a tube. And exactly the same mechanism is used for the flow of electric charge through a conductor. Here also we need to create a difference in electric pressure, and this very difference is known as potential difference. Okay. The difference of potential may be produced by a battery consisting of one or more electric cells. So we need to add a battery to so that the potential difference may be produced. Okay, the chemical action within a cell generates the potential difference across the terminals of the cell even when no current is drawn from it. Okay, potential difference between 2 points which carries some current as the work done to move a unit of charge from one point to the other. Okay, therefore we can derive the formula as V is equals to W by Q. Here it is given V is equals to W by Q. The formula will be derived. Okay, the SI unit of electric potential is volt. Electric difference is volt. It was named after Alessandro Volta. He was an Italian physicist. Okay, so here is the definition of 1 volt. Okay, this is a bit important and can be asked in example 1 or 2 marks. Okay, so 1 volt is the potential difference between 2 points in a current carrying conductor. Okay, when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. Okay, therefore 1 volt is equal to 1 joule upon 1 coulomb. As the formula for V is equals to W by Q. Okay, so unit of volt, unit of potential difference is volt, and the unit of work is joule, and the unit of charge is coulomb. So therefore 1 volt will be 1 joule per coulomb. Okay, the potential difference is measured by means of an instrument called voltmeter. Okay, we use voltmeter to measure the potential difference. Now we'll move on to the numerical example. It is a very easy example. They have given how much work is done in moving a charge of 2 coulomb. Okay, charge is given 2 coulomb across 2 points having a potential difference of 12 volt. So potential difference is given 12 volt. Potential difference is denoted by V. So V is 12 volt. We will first of all write the data. So V is 12 volt. Here they have given V is 12 volt and charge is Q is 2 coulomb. Okay, so here here they have asked work. Okay, the W is asked here. So you don't have to remember hundreds of formulas. Okay, this basic formula you know, W is equals to V is equals to W upon Q. So with this formula we will derive the charge. Okay, amount of work we will derive how? W into Q. We will multiply both of this. Okay, because W is asked, work is asked. So work is, so we can multiply, and the work is unit of work is joule. So joule is written. Okay, hope it is clear. It was very easy example question. Now we will solve the questions. Name a device that helps to maintain a potential difference across a conductor. Okay, so it will be battery or cell, which is a source of electricity. Okay, just now I have told you. Okay, see, I have told you, I have underlined also that point, that it will be, see, this is the chemical action within a cell generates the potential difference across the terminals of the cell even when no current is drawn from it. So from line by line you have to read, because from line only questions are asked. Now next question, what is meant by saying that the potential difference between 2 points is 1 volt? Just now I told you the definition of 1 volt. Okay, that is also asked from one-liner questions. 1 volt is the potential difference between 2 points in a current carrying conductor. Okay, the potential difference between 2 points. This is the 2 point of a conductor, and the potential difference between these 2 points and the current 2 points and the current in a current carrying conductor. This is a conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. Okay, so 1 joule of work is needed to move a charge of 1 coulomb, you already know, so this is called 1 volt. Okay, this is not much hard, that I'll explain you in deep. Now next question is, how much energy is given to each coulomb of charge passing through a 6 volt battery? Okay, so energy will be required of 6 joule because each unit of charge needs 1 joule of work, and this also I've told just now. Okay, our next topic is circuit diagram. It consists of a cell, a battery, a plug key, electrical components and connecting wires. Okay, so you can see here this is the symbol of electric cell, this is a battery, this is plug switch, this is open switch, and this is closed switch. Okay, this is a joint wire. Okay, and this is wires crossing joining. Okay, this is electric bulb, this is resistor or resistance, this is variable resistance, and this is Rios diagram. It will be helpful to you. Okay, this is Ohm's law. We will understand this through an experiment, but before that let's discuss what is Ohm's law. Ohm's law states that the voltage across a conductor, okay, this voltage across a conductor is directly proportional to the current flowing through it. Okay, provided all physical conditions and temperature remains constant. So it tells that the voltage V in a conductor, okay, is directly proportional to I. Okay, is directly proportional to the current flowing through it, so it is directly proportional to I. You can mathematically this relation can be described as, see, mathematically this relation can be described as V is equals to IR, R being constant, this is R is constant. Okay, then, or you can also write it as R is equals to V by I. Okay, so 1 ohm is equal to, here you can also write resistance is ohm, the unit of resistance is ohm, so 1 ohm is equals to 1 volt, okay, upon 1 ampere. Okay, so 1 ohm will be volt per ampere. Now we will start the experiment. Okay, now let's start the experiment here. In this experiment, first of all we need to arrange the experimental setup, as it is shown in this figure. Okay, first to clean the ends of the connecting wires with sandpaper and then make them shiny. Then all connections must be neat and tight. Take care to connect the ammeter, this is the ammeter and this is the voltmeter. Okay, ammeter and voltmeter with their correct polarity, positive to positive and negative to negative. Okay, then first of all you have to determine the zero error and least count of the ammeter and voltmeter and then record them. Okay, then adjust the rheostat to pass a low current. This is the rheostat, you have to adjust this rheostat to pass the low current. Okay, then this is the key. Okay, I have explained you earlier. Then you have to insert the key K, this is the key, insert the key and slide the rheostat. You have to slide it slowly. Okay, rheostat, this is, you have to slide it, slide the rheostat contact to see whether the ammeter and voltmeter are showing deflections properly or not. Okay, so next step you have to see this, and then you have to adjust the rheostat to get a small deflection in ammeter and voltmeter. Okay, you have to adjust this rheostat. Then first of all you have to first use only one cell. Okay, you have to use one cell. Here you have to use only one cell as the source in the circuit. Now you have to note down the reading in the ammeter I for the current and the reading of the voltmeter for the potential difference. Voltmeter is used for potential difference and ammeter for current across the nichrome wire XY. Okay, this is the place for the nichrome wire. Okay, so then record the readings of the ammeter and voltmeter. You have to take at least 6 sets of readings by adjusting the rheostat gradually. then you have to plot after this doing this, you have to plot a VI graph here like this one. Okay, like this one you have to plot a VI graph along x-axis and y-axis respectively. Okay, then in this experiment you will notice that the values for VI here, the values for VI, okay, the values for VI is always same, it all will be same, and the VI graph is a straight line that passes through the origin of the graph, and thus VI is a constant ratio. And here you have seen that the VI graph passes along a straight line. Okay, so thus this is a constant ratio. Okay, so this Ohm's law was found by is a relationship between the current and the flowing metallic wire, and was founded by George Simon Ohm. He was a German physicist. Okay, and these derivations I have told you earlier only. Okay, now we will come to another activity. In this activity we have to arrange the setup as shown in this figure. We have to arrange the setup as this. Okay, this is the, again I'm telling you, this is key, this is cell, this is ammeter, and this is XY. Okay, now we will see the activity. Okay, we have to set the circuit by connecting 4 dry cells of 1.5 volt each in series. These are the volt. Okay, you have to connect these volts in dry cells of 1.5 volt. These are the dry cells. Okay, you have to connect this in series with the ammeter. Okay, this is the ammeter, you have connected it in series, and then you have to leave a gap of gap between x and y as shown here. This is the gap between x and y, and you have to leave a gap. Likewise you have to set make the setup. In the next step then you have to complete the circuit by connecting nichrome wire in this gap and then take the ammeter reading. Here in this gap xy, you have to place this nichrome wire. Okay, this nichrome wire you have to put here, and then you have to take the ammeter reading. Okay, so then in the next step, after taking the reading of the ammeter, after putting nichrome wire, you have to again replace this nichrome wire. This nichrome wire you have to replace with the torch bulb in the circuit. This torch bulb you have to put here torch bulb in the circuit and find the reading of the ammeter again. Okay, this is the next step. And in the third step, you have to repeat this setup with 10 watt bulb. This you have to replace this torch bulb with this 10 watt bulb. Okay, now in this activity you will notice that the current is different for different components. It will be different for nichrome wire, different from for 10 watt bulb and torch bulb. Okay, and this is just because certain components offers an easy path to flow of electric current with others resist the flow. Okay, and thus the motion of electrons through a conductor is retarded by its resistance. Component which offers low resistance is called good conductor, whereas component with high resistance is called poor conductor. Okay, now there is again an experiment to study the factors on which the resistance of conducting wires depends. First of all, arrange the apparatus as shown here in the figure, consisting of a cell. This is a cell, and this is the nichrome wire, the pointed with 1. This is the nichrome wire of between 2 points of length L. Okay, and the plug key. Okay, and ammeter. First of all, plug the key, then note the current in the ammeter. First of all, you have to plug the key and then note the current in this ammeter. This is the ammeter. Okay, then you have to replace this nichrome wire. Okay, this nichrome wire you have to replace by another nichrome wire of same thickness. Okay, same thickness and twice the length, that is 2L. This length was L, this length was L. Okay, and you have to replace this nichrome wire's length by 2L. Okay, then again you have to note the ammeter reading with this length, 2L length. Okay, now again next step, you have to replace the wire by a thicker nichrome wire of length L, then again note the ammeter reading. The next step is you have to replace this 2L length with thicker nichrome wire length, okay, and length should be L, not 2L, okay. Length will be L and of thicker nichrome wire. Then again you have to note the ammeter reading. Next, in the next instead of nichrome wire, you have to connect a copper wire in the circuit, okay. Here in the copper you have to connect copper wire. Which wire? Copper wire, okay. Then of length L, length should be L, and of the same thickness will be same. And then you have to note the value of the current, like ammeter reading you have to note. Then you have to note the difference in the current in all the cases. All the 4-5 readings what you have taken, you have to note the difference in all the cases. And now you will observe that the ammeter reading decreases to 1/2, okay. It decreases to 1/2 when the length of the wire is doubled, okay. You have to remember this. If the length of the wire was doubled, the ammeter reading decreased to 1/2, okay. And the ammeter reading increases when a thicker wire of same length and material is used, okay. So you can notice the changes in the ammeter reading, okay. Therefore we can conclude that the resistance of a conductor depends on its length, on its area of cross section. Length, this was the length, this was the length, okay. Area of cross section, area of cross section means thickness of this, okay. This is area of cross section. On the nature of its material, whether it is a nichrome wire or a copper wire, okay. On the nature of its material. So resistance of a wire depends on 3 factors: on its length, on its area of cross section, and on the nature of its material, okay. Resistance of a conductor is directly proportional to its length. So resistance is of a conductor is directly proportional to its length. So you can write it as R into L. Let me show you. See, resistance is directly proportional to its length, so it will this is the sign of proportionality, okay. This is the sign of proportionality, and you will write here directly proportional to L. So it means that as the length increases, if length of a wire increases, resistance also increases, okay. You can take the example, if longer the road, the more the traffic, okay. If the road is longer, the more will be the traffic. So you can likewise you can learn this, okay, that the more there is length of the wire, the resistance will increase, okay. Next one. And next, resistance of a conductor is inversely proportional to its cross sectional area. You can see here it's inversely proportional to its cross sectional area. If something is inversely proportional, then you will write this is the proportionality sign, you will write it 1 upon, okay. So it is inversely proportional, cross sectional is inversely proportional, so upon A, okay. So resistance is inversely proportional to its cross sectional area. So if we combine the both the equation this 1 and 2, we will get resistance is inversely proportional to A and directly proportional to L, okay. So here you can remove this proportionality sign by a constant of proportionality. This is called rho, okay. Here it is written also, it is called rho. This is constant of proportionality, okay. You can also call this electrical resistivity of the material of the conductor. This rho is called electrical resistivity of the material of the conductor, okay, or constant of proportionality, either you can say. So you can remove this R with rho. So R is equals to rho L into A. This formula will be helpful for you in your ray diagrams, okay. So this formula will be helpful for you in your ray diagram. You have to remember this formula, and sorry, not in ray diagram, in numericals, okay. And you have to put the value of this constant of proportionality, and you have to solve the numericals. Now we'll move to the, then here in the in this table, electrical resistivity of some substances have shown, which reveals that the resistivity of an alloy is generally higher than that of its constituent metals. You can see the electrical resistivity of these substances, and you will notice that the resistivity of an alloy is generally higher than that of the constituent metals, okay. See, now we'll move to the exemplar questions. So this is question number 1, example 12.3. In it, it has asked how much current will an electric bulb. So in example 12.3, it is asked that how much current will an electric bulb draw from a 220 volt source. So first of all, you'll write the data what is given. So volt is 220 source, 220 volt. Okay, volt is 220 volt, and if the resistance of the bulb filament is 1200 ohm, unit of resistance is ohm, so resistance is 1200 ohm and V is given. So you have to find out current, sorry, you have to find out the current of the electric bulb. So I you have to find out, so I is equals to V by R, and you can solve this numerical very easily. Okay, it was a easy numerical. You will divide 220 by 1200, and so it will come 0.18 ampere. And there is also next question B, how much current will an electric heater coil. Okay, note the difference, here is electric bulb and here is electric heater. Okay, electric heater coil draw from a 220 volt source, and if the resistance of the heater is 100 ohm. Okay, so again you will find out this current, and here current will come 2.2 ampere. Remember that you have to always mention the unit of, if you take out anything. Likewise here current, okay, you have to mention the unit of current, ampere, otherwise you will not get marks. Okay, so you can note here the difference that the electric bulb, current drawn from electric heater and electric bulb. Okay, electric bulb takes more heat than electric heater takes more heat than electric bulb. Okay, so it was an easy question, you just have to find the current. In exams this much easy questions doesn't come. Okay, so prepare for much harder questions. Okay, tougher questions you should prepare. Example number 12.4 is just a basic idea. It's given in these examples. The potential difference between the terminals of an electric heater, okay, is 60 volt. What is potential difference? First of all, I explained you that the potential difference, the definition of potential difference was, potential difference is the difference of electric potential between 2 points. Okay, so here is given volt, 60 volt, like the potential difference between the terminals of an electric heater is 60 volt. Okay, you will first of all write the data again. So volt is 60 volt. When it draws a current of 4 ampere, current is 4 ampere from the source, what current will the heater draw if the potential difference is increased to 120 volt? First of all, you have written here 60 volt. First of all, you have written here 60 volt, and this current is 4 ampere. Okay, so according to Ohm's law, you will apply Ohm's law. Okay, so according to Ohm's law, R is equals to V by 1. So V by 1, resistance you will find out 15 ohm. Okay, then when the potential difference is increased to 120 volt, okay, the current is given by, so you will take out I is equal to V by R. So here you will take out. Okay, this is such a simple example. Okay, here in this question you didn't know R, so first to take you have to take out R according to Ohm's law. Then you have taken out R, then current automatically comes out. Okay, the next example will move on. Example 12.5. So this is example 12.5. In here, resistance of a metal wire of length 1 meter is 26 ohm at 20 degrees Celsius. Here length is given, that is 1 meter. Okay, length 1 meter L, and is 26 ohm. This is resistance is 26 ohm at temperature 20 degrees Celsius. If the diameter of the wire is 0.3 mm, it has given diameter, it means cross sectional area. So what will be the resistivity of the metal at that temperature? Okay, using table 12.2, just I have now I've shown you the table. That table you have to see and predict the material of the wire. So here R is given, so they have written R. Okay, 26 ohm. Then diameter of the wire, that is D, is 0.3 mm, and you will convert it into meter. So it will be 3 into 10 to the power minus 4 meter, sorry. Okay, if you want to convert mm into meter, so you will multiply it with 10 to the power minus 4 meter. So it will come, then length is given 1 meter. Okay, and according to the law, Okay, resistivity of given metallic wire is rho is equals to Ra upon L. Just now I've told you the formula. It came that R was directly proportional to L. Okay, wait 1 minute. See, R was directly proportional to L, then R was inversely proportional to its cross sectional area. So with this you can conclude that R is proportional to L upon A. Okay, so with this you have taken out the formula, that R is equals to rho L by A. Okay, this only they have multiplied here, and they have, see here, they have multiplied rho is equals to Ra upon L. I hope you have understood this. Okay, so A cross sectional area is this, A is cross sectional area. So for this they have converted it into pi into d square. Okay, pi into d square upon 4L. Length will be doubled 4L. Okay, so here the formula for area of cross sectional area is pi d square upon 4. Okay, so according to that, R A pi d square upon 4L. Okay, so substituting the values you will get rho is equals to 1 by 1.84 into 10 to the power minus 6 ohm meter. Okay, so you can understand here that the rho is 1.84 into 10 to the minus 6 ohm meter, and the resistivity is of manganese. Okay, we'll move on to the next question, if there is any. One more question. A wire of given material having length L, length is L. First of all you have to write the data. So length is L and the area of cross section A has a resistance of 4 ohm. Okay, what would be the resistance of another wire of the same material having length L by 2 and area of cross section 2A. So length is halved and cross section is doubled. Okay, so first of all we will not focus on this second question. First of all we will focus on this first question. Okay, so for the first wire, okay, here it is written for the first wire, rho resistance is rho into L by A, that is 4 ohm. Okay, resistance is given here 4 ohm. So according to the formula, rho into L by A is 4 ohm. Now for second question, here it is given for it is asked the resistance, it is asking for second wire. Okay, so for R2 you will, here you will write R1, and for second wire R2 is rho upon rho into L by 2, means length is halved and this thickness cross section area is doubled, so it comes 1 by 4 is equals to rho into L upon A. Okay, so rho 2 comes 1 by 4 into R1. R1 is rho 1 by A, so 1 by 4 into R. I think you are understanding this. So the resistance of the new wire is 1 ohm. Okay, hope it is clear. Now we'll move on to the questions, which are extra questions, and these are also very important questions, and it will just test what you have just read. It's not so difficult questions. So first question is, on what factors does the resistance of a conductor depends? So this one I've told you just now, that the factor resistance of a conductor depends on its length. Okay, length, then area of cross, this is length. Okay, this is length, then area of cross section, it depends on area of cross section, this is area of cross section, and on the nature of the material, of what nature, or whether it is a nichrome wire or a copper wire. We have done the experiment. Okay, according to that one, so it was easy question. Now we'll move on to the second question. Will current flow more easily through a thick wire or a thin wire of the same material when connected to the same source, or why? So just now I told you that the resistance of a conductor is inversely proportional to its cross sectional area. Okay, so the answer will be why, because if one increases other decreases. Okay, now next question, let the resistance of an electric, So we'll move on to the next question, that is, let the resistance of an electrical component remains constant. Okay, resistance remains constant while the potential difference V across the two ends of the component decreases to half of its formal value. What change will occur in the current through it? So I'll be solving this third question here. Okay, pay attention. Okay, so first of all they have said let the resistance of an electrical component remains constant. R will be constant while the potential difference V across two ends of the component decreases to half of its former value. And what change will occur in the current through it? So first of all we'll see, first of all we'll see that the original formula for V is equals to IR. Okay, this you know. Now if you can change this formula, okay, as V I is equals to V by R, because you have to find the I. Now V naught will be half of its former value. Okay, so it will be 1 by 2 into V. Former value is V, so 1 by 2 into V. Okay, now next will be, you have to find out I naught. Okay, so I naught will be, please adjust here, no place, so I'm doing it here. Okay, so I naught will be V naught upon R. Okay, so V naught is 1 V by 2, V naught is V by 2 upon R. Okay, so here you will find that I naught will be 1 by 2 into I. How come? Let me see. This is I naught. I naught is equals to V naught by R. Again I'm solving because of I naught is equals to V naught by R. So I naught will be V by 2 upon R. Okay, V by 2 upon R. Then again I naught will be 1 by 2 in, okay, 1 by 2, sorry, here bracket will be 1 by 2 into I. What is I? I was V by R, so V by R you can take out. Okay, and 1 by 2 will be different, separate. Okay, so I naught is equals to half 1 by 2. So the answer will be what? This is asked in last, what change will occur in the current through it? So current will be reduced to half. Okay, I hope this is clear. If not clear, please stop the video, rewind the video, again see the video. Okay, now next question, fourth one. Why are the coils of electric toaster and electric irons made of an alloy rather than a pure metal? I just told that the resistivity of an alloy is generally higher than that of its constituent metals. Okay, in that table I have told you, that will be the answer. Okay, now use the data in table 12.2 to answer the following: which among iron and mercury is better conductor, and which material is the best conductor? So this both parts you have to do by seeing the table 12.2, and you have to do it by your own. This both of the questions have to by your own, and you have to write the answers in the comment section. I will see it. Okay, each and everyone write those answers, both A and B. Put A and then B and then write it in the comment section. Okay, I will read it. Okay, everyone's answer I will read it. So till here I have completed everything, like resistance, charge, electric current, potential difference, on what resistance of a conductor depends. Everything I have taught you till here, and again in my next video I'll be continuing this chapter from the very next topic. And so please stay tuned, and if you understood my way of teaching, please hit the like button and subscribe to my channel, and please keep supporting me. Thank you.